Okay, in this problem, we're going to look at the final set of hypothesis tests that you'll come across in public sector work or work for a corporation where you're doing analytics. These tests involve variances. In this example, General Gas manufactures natural gas baking ovens. If the ovens are set to 350 and then heat up to 350 degrees and then remain exactly at that temperature until they are shut off, the standard deviation would be 0. That is not how the ovens work, though. The flame in the oven turns off when the temperature inside rises above its setting. So maybe the flame turns off at 355. And then the heat escapes the oven naturally through the door and the seal. And maybe the oven reignites when you get to 345. So the oven is constantly cycling on and off. So that suggests there's a standard deviation, right? Because the temperature varies, right? It's not exactly 350 all the time. Now, changes to the quantities of ingredients in the batter and ovens with excessive oven temperature variation can produce cookies with inconsistent taste. Cookies can burn if the oven does not maintain a constant temperature, or may not be sweet enough if only 8 cups of sugar are added instead of the 9 cups recipe calls for. Now, an industrial trade publication tests natural gas baking ovens and recommends the ovens to bakeries if a random sample of 30 of a manufacturer's ovens set to 350 degrees for 60 minutes in a test room has an average temperature of 350 and a standard deviation under 5 degrees. Both conditions are going to be tested at 5% significance because that's the industrial trade publication standard. The first column of the table at the bottom of this problem reports the recorded temperatures of a random sample of General Gas ovens in such a test, right? So I'm going to go ahead and copy the data down here. The first column is General Gas. The second column is Maytap, a competitor, right? And then, of course, I'm going to grab like the word submit. I'm going to press Control C on a PC. With Mac, you can press Command C. And I'm going to paste that information in the third worksheet of our template. I'm going to right click or 2-finger click and then the mouse. I'm going to pick match destination formatting. Okay, and I'm going to call this set of values. I'm going to call this set of values. So I'm going to highlight the numbers, the 30 numbers under gas, General Gas. I'm going to call it GG. And then I'll call Maytap MT. Call Maytap's 30 numbers MT. Okay. And then I'll go back up here. Now, I'm giving you results of a one-mean test that has already been completed. The test statistic and the p-value were equal to negative 0.696. So I got to change this to negative 0.696. I got to change the p-value to 0.492, right? And notice that there's no population standard deviation given here, right? So we had to use a t-distribution to calculate this mean here, right? We're using a t-distribution to calculate this mean. So I can find the p-value because we don't know the population standard deviation. We have to use a sample standard deviation. We're going to use a t-distribution. I can actually calculate this value using a t-distribution. T.dist, and we're going to use this because test statistic is the number on the number line. Notice it's negative, right? And this is a two-tailed test. It's a two-tailed test. So if this were positive, we'd want to make it negative, right? But since it's negative, we're gonna just type it in as a negative 0.696. The degrees of freedom here are 29 because we have 30 in our sample, right? And then I need to do true. Now, because this is a two-tailed test, I got to multiply this by 2. And in fact, I get 0.492, right? 3 decimal places. I actually get it to 4 decimal places, right? So this is what was given in the problem, and this is me calculating it, right? So let me open up statsdistributions.com. We'll go back to the T distribution, student T. And our degrees of freedom were, again, 29 because we had 30 in our sample, right? And our test statistic was a negative 0.696. So I'll copy that, put that in the T value. And it's a two-tailed test, right? So if I put in the positive value, right? I put in the positive value, 696. If I put in the positive value, right? Excel would have gave me this value, right? So if I make this negative, negative 6.696, that's the value I want, and then it's a two-tailed test, right? So a two-tailed test, I have a negative 6.96 and a positive 6.96, right? And then these two added up is 0.492, right? 0.492. Okay, now what about the critical value? Well, let's see what it looks like in statdistributions.com. I'm going to change this to 0.05, right? And this is a negative 2.046. This is a positive 2.46. And the probability of being outside those numbers is 0.05. Half that 0.05 is here, and half that 0.05 is here. So since this is a two-tailed test, I'm going to divide the alpha by 2. I'm going to divide this alpha by 2. So this is the probability of being in that lower tail, right? 0.025, right? So this is 0.025 or 2.5%, and this is 2.5%. 2.5 plus 2.5 is 5%, right? 5%. Okay, so now I'm going to do equal. Again, this is a T distribution. T dot dist. T dot dist is when I input number on the number line. I'm putting in a probability, right? So I need T dot inverse. And the lower tail probability is 2.5% or 0.025. And the degrees of freedom are 29 again, right? And I hit enter. And I get a critical value of, to 3 decimal places, negative 2.045. Okay. So what is the conclusion of my test? My test statistic is a negative 0.696, right? So the difference between the sample mean and 350, that difference, right, is negative because the test statistic is negative. So my sample mean is less than 350, right? I can show you real quick what it is. Down here, the sample mean is 3.49, $349.37 degrees, right? So the sample mean is less than that, right? Which is why the test statistic is negative. So the difference between my sample mean and my hypothesized mean is negative, right? The next question is, so the test statistic is on this side of the distribution because it's negative, right? The next question is it significant? Well, it's a negative 0.696. Well, negative 6.96 is not under the significance area. If it was out here, it would be negative and significant. but it's right here, so it's negative and insignificant. And the null hypothesis is the difference is 0, right? The difference between my sample mean and that is 0, right? So this is my do not reject the null region. So I'm gonna not reject the null. We cannot reject the null, right? At 5% significance, we cannot reject the null hypothesis. So what that's saying is the sample average, which is 349.367, it's really close to 350. So we're going to conclude that the null is probably true, right? We have evidence to support the null. So we're going to say, whoops, I'm too low. Up here. Sorry. We cannot reject the null up here. I'm in the wrong test. This is another test. I got to be up here, right? I'm doing the one mean test up here, right? So at 5% significance, we cannot reject the null hypothesis. In other words, what we're saying is our evidence supports the null hypothesis that our average is 350 degrees Fahrenheit, right? Now we're going to complete the one variance test to determine if the standard deviation of general gas ovens is under 5 degrees Fahrenheit, right? Now, this statement is the statement in bold letters, bold font. The standard deviation, right, which is sigma. The standard deviation is sigma, which we cannot know. Sigma is under less than 5 degrees Fahrenheit. Well, that's the alternative hypothesis. Except in order to be the alternative hypothesis, we have to square this, right? So if we square this, we get the sigma squared, right? Well, if we're squaring that, we have to square the 5, right? Because the standard deviation under 5 is equivalent to the variance under 25, right? So this statement is the alternative hypothesis if we square that and we square this, right? And then the null hypothesis is the opposite, right? So the opposite of sigma squared less than 25 is sigma squared greater or equal to 25, right? And the null always includes the equal sign. Now this test is a lower-tailed test. It's a one-tailed test, but it's a one-tailed test that's pointing to the left. So that's a lower-tailed test, right? Now the sample size, we're going to type equal. Oops. This is, we got to change this right here. This is for our one variance may general gas test, right? So this is the general gas one mean test. And this is the general gas one variance test. And we got to change this to greater than or equal to. So I'm going to type the greater than symbol. I'll do Control U for underline. And then the alternative hypothesis is less than, right? And this is the 5 squared, right? 5 squared, which is also 25, right? Now we need a count. We already know it's 30, but we're going to do equal count. I like to use count A. And we're going to type GG for general gas. So that's going to count those things in the blue box, right? And that's 30. Let me go ahead and delete this down here. Submit question 3. Okay, that makes sense, right? Now the degrees of freedom again are what? N minus 1. Now we're going to calculate the variance of the sample. Because remember, we don't know the variance. The variance is unknown. It's the variance of the sample, so we're going to type equal VAR dot S. And then we'll do GG for general gas, right? This is the variance of the sample. because we don't know the population variance, but we know the sample, we can calculate the sample variance. We had to use a t-distribution up here, right? That's why we had to use a t-distribution up here, right? All right, now we got to do the test statistic. So the test statistic for this is a chi-square test statistic because we're talking about squared values, right? Sigma squared is squared. So we're going to use the chi-square distribution. Now, we're going to use dot dist because we need a number on the number line. And the number on the number line is, whoops, sorry, getting ahead of myself. The test statistic is the sample variance, and divide the sample variance by hypothesized variance. So we're taking the sample variance and divided by the hypothesized variance. And notice my sample variance is pretty close to the requirement of the trade magazine. It requires it to be 25, right? So this ratio is close to 1. But a one variance test statistic for a chi-square distribution, the one variance test statistic is the ratio of the variance from the sample divided by the hypothesized variance times degrees of freedom. Now, because sample variance rounds to 25 with 0 decimal places, the test statistic is going to be really, really close to the degrees of freedom of 29. Of course, when this test statistic is really close to the degrees of freedom, what that's saying is the difference between the sample variance and the hypothesized value is really small, close to 0. So this minus that is close to 0, but our test statistic is this divided by that. So when there's no difference in two numbers, that means the ratio of those two numbers is really, really, really close to 1. And since we multiplied the ratio of those two variances, one being the sample, the other being the what it's supposed to be according to Trade Magazine, because that's really close to 1, the test statistic is really close to the degrees of freedom, right? So if we round these to 0 decimal places, you can see the test statistic is equal to degrees of freedom. So what that means is the degrees of freedom is the center of the distribution. Unlike the t-distribution or the standard normal distribution, the center of those distributions is 0 because we're looking for 0 difference. Here we're looking for a ratio equal to the degrees of freedom. So the center of the chi-square distribution is the degrees of freedom. But we want this in terms of 2 decimal places. I mean, 4 decimal places. Okay, again, we need 4 decimal places for non-integer values. Oh, and p-values to 4 decimal places and all non-integer values to 3 decimal places. So the p-values, these are 3 decimal places. And the p-values are 4 decimal places. Okay, so the p-value, we're going to look at it. We're going to look at it in statdistributions.com. Let's go ahead and fill in some information here. The sample size is 30. Degrees of freedom are 29. The sample variance is 24.861. Mine's 24.861. My test statistic is really close to degrees of freedom because the sample variance is really close to the hypothesized variance. Now we gotta get the p-value, right? So let's press enter to see what we got. Everything looks good, right? So that's cool. All right. Now we gotta get the p-value, right? So we're gonna open up the statdistributions.com calculator, go back to chi-square distribution, and we're gonna use 29 degrees of freedom. Notice it kind of looks bell-shaped, right? this is a very thin tail, and this is a very thick tail. So it's not symmetric, right? And notice the degrees of freedom here are 29. Because this is thicker than that, the 29 is just to the right of the hump, right? So when the sample variance equals the hypothesized variance, that ratio is close to 1. But then when we multiply by the degrees of freedom, we get a value that's going to be inside the hump, right? Now, this test is a lower-tailed test, right? So because it's a lower-tailed test, we're going to use the left tail. Left for lower, right? So we're going to use a left-tailed test. The significance level is 5%. So 5%, we'll go ahead and get the critical value from statdistributions.com. So the p-value, the alpha level is 5%. And it's a lower tail test. So we choose the left tail. And it looks like the chi-square value is about 17.71. The degrees of freedom are 29. Okay, so that's our preliminary critical value. It's not going to be our final critical value. We're going to get it from Excel. All right, now we got to get the p-value, right? And the test statistic is 28.839. So we're going to copy that into statdistributions.com and replace the chi-square value, the number on the number line, with it. Again, we want the left tail because it's a lower tail test. And the p-value, the preliminary p-value is 0.0526. Again, we're going to double check that with Excel, right? So with Excel, we're looking for something close to 0.526. I'm going to type equal chi-square. I'm not going to do right tail because this is a left tail test, right? A lower tail test. So I'm just going to use the chi-square.dist function. And the number on the number line is the test statistic. And then the degrees of freedom are 29. And then in Excel, you got to type true. In Google Sheets, you have to type true. And we get something really close to the 0.526 that we saw in statsdistributions.com, right? Except we need it to be more accurate. We got 0.5265, right? Now we need to do the same thing for the critical value, right? So the critical value, the input to it is a probability value, in this case, 5%. We're going to use chi-square, and we're going to use dot inverse, not dot inverse dot RT, because that corresponds to a right tail test. We want the left tail test, right? So we're going to use chi-square dot inverse. And then we're going to click on the probability value that corresponds to the area in the lower tail of the distribution, right, which is our significance level. And we're going to click on the degrees of freedom and then hit enter. And we get something close to what statdistributions.com gave us, right? But we need 3 decimal accuracy, not 2, right? So now we got the answers, right, to our test here. So let me go back to math. Oops. So our p-value is 0.5265. Hit enter and it should get right. Right. Now we got to figure out what the result of our test is, right? Now, let's go back to the significance level of 0.05. Okay, so this right here, our significance level is 0.05. So this area is our significance level, right? If our chi-square test statistic is under the blue area, right, then our ratio is going to be less than the degrees of freedom, right? Or I should say less than 1, right? Our variance, if our test statistic is under the blue area, then this divided by that would be the difference between this and that would be significant. The ratio would be significant. The difference would be significant. But that's not the case because the test statistic is 28.839. It's about the equal to the degrees of freedom. So this is the reject the null region here, right? Under the blue area, because this is significance. This is a negative significant difference, right? We're under the white area, so that's the cannot reject the null region, right? So if your test statistic is less than this critical value of 17.71, then you would have a negative significant difference. Our difference is negative, but it's insignificant because it's so close to this value 25, right? So we cannot reject the null here. We cannot reject the null hypothesis. Now, what does that mean? When you cannot reject the null, you're saying the data suggests that this is true, right? Our data is suggesting this is true. And what does this mean that it's true? Well, the variance is equal or greater than 25, or the standard deviation is equal to or greater than 5, right? So we can't say it is, we can't say the standard deviation of gas ovens is greater than 5. Well, we can't say that because the null hypothesis is greater than or equal to. So we can't say, now this one is greater than or equal to 5, right? We can't say it is 5 degrees Fahrenheit or higher, right? We can't say it's too strong. We can't accept the null hypothesis. What we can do is we cannot say that the alternative is true. And the alternative being true is less than 5 degrees Fahrenheit, right? So one selection, which is not here, would be we cannot say the thing in blue, right? Our evidence, the data suggests, or according to the data, we cannot say the standard deviation of general gas ovens is less than 5 degrees, right? But that's not a choice. So we have to go with appears to be at least 5 degrees Fahrenheit. Appears, that's the softest statement, right? So we're gonna go with appears to be at least 5 degrees Fahrenheit. Again, we can't state that the null is true, right? All we can say is we cannot reject it, right? And rejecting it would be to say the alternative is true. So if we have evidence to support this, what we say is we cannot reject this, right? We cannot reject that. All right, so that's the one variance test, right? That's the one's variance test. Now, because we could not reject this, okay, so the trade magazine, okay, the trade magazine says what? You get a thumbs up in the trade magazine if the average temperature is 350 degrees, right? And we concluded that the data suggested from our sample that that probably is true. But in our one variance test, our evidence didn't support the alternative, it supported the null hypothesis. So we would not get a thumbs up or recommendation from this industrial trade magazine because we want the evidence to support the alternative hypothesis on the one variance test. And we want it to support the null hypothesis on the one mean test, right? So this we check the box here, but we didn't check the box here, right? Because we concluded that this one's probably true, right? So we only got one of the two standards satisfied. We got the one mean test satisfied, right? Now, this is another problem that we could do, right? So General Gas has marketed its ovens to bakers all across the United States by claiming they are less expensive and just as consistent as industrial leader Maytap. Now, since General Gas ovens are much cheaper than Maytap's, right? All we need to do to support this claim in our advertising is complete this two variance test below to determine if the rest of the marketing claim is valid, right? And consistency implies a small standard deviation. But when you're comparing your standard deviation to a competitor's standard deviation, right? And you're saying it's just as consistent, what you're saying is your variance is equal to their variance. So that would be our null hypothesis. So the other part of our marketing claim is just as consistent, which means the variances are equal. Now, this is the null hypothesis. It always includes the equal sign. So the alternative hypothesis is not equal to. And not equal to is the same thing as saying one variance is less than the other, or the other variance is greater than the, right? So we're saying either this is less than or it's greater than. Less than or greater than is not equal to, right? I like this. I like using this instead of the equal sign with a slash in it because it's pointing to the lower tail test and it's pointing to the upper tail test. So this is a two-tail test. Let's hit enter to make sure we got everything right so far. Okay. All right. So I got the stuff for General Gas, right? Oh, let me fill it in right here. I'll go ahead. I'm going to maximize this in the screen so you can all see it, and we'll finish this off here. So we're saying equals here, right? And we're saying not equal here, right? Less than, greater than, which is the same as not equal to, right? And then for General Gas, we have equal count A, GG. For Maytap, we have equal count A, MT, right? Our degrees of freedom are n minus 1, right? Then we got to do our variances, right? So we're going to do equal variance of the sample. So VAR dot S, GG for General Gas, and then equal VAR dot S for Maytap, and Maytap is MT, right? We named those numbers MT, remember that? Yeah. Now we got two variances here, right? Two sample variances. And the test statistic for two sample variances is we take the bigger one and we divide by the smaller one. So the test statistic is always going to be greater than 1 here, right? Because we're taking the bigger sample variance and we're dividing by the smaller sample variance. And notice how close it is equal to 1. Oh, and these values got to be to 3 decimal places, right? Okay, so we're taking this sample variance and divided by that sample variance because this is the biggest one, right? So this is our numerator. So up here I'm going to put in parentheses numerator. And then here I'm going to put in parentheses denominator. That doesn't really matter because our degrees of freedom are the same, right? I'm only doing this if our degrees of freedom are different, but they're both the same because both sample sizes are 30. So this is our biggest one. So that goes in the numerator of the test statistic. And this is a smaller of the two variances. So it goes in the denominator of the test statistic, right? So again, our F statistic is going to be bigger. Our test statistic here is going to be bigger than 1, right? When there is no difference between two things, the ratio is 1. So because the ratio is really close to 1, the difference is really close to 0, right? Now, the ratio of two variances follows an F distribution, right? So now I'm going to go to statsdistributions.com. I'm going to click on the F distribution right here. So the last one is the F distribution, right? Okay, now this is a two-tailed test. The problem with the F distribution in stats distribution is it only gives you a right tail or a left tail, okay? Now, because we put the bigger variance in the numerator, right? Because we put the bigger variance in the numerator, right? Let me put the degrees of freedom in real quick. So this is 29 and this is 29. Notice it kind of looks like a chi-square distribution with like 29 degrees of freedom. But notice the hump is near 1, right? 1 is about here, right? 1 is about here. And it's not quite in the center of the, at the peak of the distribution, right? And that's because this tail is really thick and this tail is really thin, right? So 1's right about here, right? And if there's no difference in the sample variances, we're going to be right here in the middle of this distribution, right? Now, because we're putting the bigger sample variance in the numerator and the small in the denominator, this will never be less than 1. We're never going to be down here, right? So because this is bigger than 1, we need the upper, we need the right tail of the distribution, right? The right tail of the distribution. Okay, so the test statistic here is 1.006, right? Now, the p-value, if this were a one-tailed test, the p-value of the test statistic would be 0.494, right? But it's not a one-tailed test. It's a two-tailed test. So we got to add this tail to this tail over here, okay? And because this is always bigger than 1, we don't really have to worry about this tail over here, right? All we got to do is multiply this by 2, right? And one way to see this is to take this variance, the smaller variance, and divide by the bigger variance. And you get 0.994, right? What I can do is I can flip this around. I can do 0.994, and I can do left tail, right? So notice the probability. It's still 0.494, right? So that's that. This right here would be the lower tail that we'd add to the upper tail. And 494. So we add those two together because it's a two-tailed test. Or we could just simply multiply it by 2, right? So the p-value here is 0.494 times 2, right? But again, statsdistributions.com is not exactly accurate, right? So what we want to do is we want to calculate, we're going to use f dot dis, because we always divide the bigger variance by the smaller variance. We want not f dot dis, but we want f dot dis dot rt, right? We're going to click on that value, and then we're going to do the numerator degrees of freedom. Remember, this is the bigger variance, so this is the numerator degrees of freedom, and this is the denominator degrees of freedom, right? And then we hit enter, and we get 0.4934. But again, this is a two-tailed test, right? Because it's a two-tailed test, we got to multiply this by 2. Because there's tail over here too, right? There's a tail over here. So the p-value is actually 0.9867, right? Now, what we want to do is we want to find the critical value, right? We want to find the critical value. And this is a two-tailed test. What do we have to do? We have to divide the alpha by 2, right? And then we have to divide this 5% by 2. This is a two-tailed test, right? So the significance level is 5%, right? But half of that is in the upper tail and half that's in the lower tail. So let's look at that. So half of it is going to be in the lower tail, right? That's the upper tail right there, right? So half of the 5% is here. The other half of the 5% is here. So this is 0.025. And that's 0.025, right? But because we always put the bigger variance in the numerator and the smaller variance in the denominator, we don't really have to worry about the lower tail, the left tail. We don't have to worry about that. We don't have to get the critical value down here because we always put the bigger variance in the numerator and the smaller variance in the denominator. So the F statistic will never be down here, right? If we didn't do that, if we put the smaller one in the numerator and the bigger one in the denominator, then we have to find the lower critical value, right? But we don't really have to worry about the lower critical value because we always put the larger variance in the numerator and the smaller variance in the denominator, right? So my critical value should be 2.101, right? So again, we're using the upper tail, right? So we're going to do F dot inverse because the input to this is a probability value, the 2.5%. But again, because the test statistic is bigger than 1, will always be bigger than 1 because the bigger variance is in the numerator and the smaller variance is the denominator, we use .RT, right? And I'm going to click on the 2.5% because that's the area of the distribution, area under the distribution. The numerator degrees of freedom were 29 because this is the bigger variance, comma, the denominator degrees of freedom because this is the smaller variance, and that's in the denominator of the F statistic. And then, and then I'm going to hit close parenthesis and hit enter. And our F critical value is equal to the F critical value in statdistributions.com, right? So let's go back to my open math and fill in the information. So both sample sizes were 30. Both degrees of freedom were n minus 1 or 30 minus 1, 29. The variance of general gas was less than the variance of ATAP, but not by much. Ratio of those two, the bigger one divided by the smaller one, was slightly bigger than a 1. Again, a small difference in Maytap and general gas variances means their ratio is going to be really close to 1, and it is really close to 1. The p-value is 0.9867 in my problem. Okay. Go ahead and hit enter. Okay, now let's go into statdistributions.com, right? Now, where's my test statistic? My test statistic, now you got to imagine there's a blue area down here, right? We don't have to do it because, again, the test statistic will always be greater than 1, right? But it's really close to 1, right? It's not under the blue area of the lower tail and the blue area of the upper tail, right? It's under the white area, 1.006, right? If it were, say, 2.301, if my test statistic was here, it would be under the significance level. If my test statistic was like 0.1, you got to imagine there's a blue area here, right? It would be under the significance level. But it's not in either tail. It's in the hump of the distribution. So it's in the region that we do not reject the null, right? So we're not rejecting the null here. So we're not rejecting the null. Oh, we already did that, right? Cannot reject the null. The test statistic is got a p-value that's 0.967. The bigger the test statistic is, the more evidence we have, or sorry, the bigger the p-value we have, the closer the test statistic is to 1, right? It's closer to 1, which means these two things, their difference is really close to 0. So as this p-value gets bigger, this difference gets smaller, right? Or their ratio gets closer to 1. So what we're concluding here is that the variances of these two manufacturers are probably equal. So that's why we cannot reject the null hypothesis, right? Our evidence is saying these two are equal because their difference is close to 0. Their ratio is close to 1, right? So what does that mean? Well, we can't accept this, right? We can't say that the variances are equal. Or if we say the variances are equal, we're saying are as consistent, right? We can't say general gas ovens are as consistent as Maytap ovens because we concluded that this is probably true, right? If we conclude that this is true, we can say that, but we can't conclude this is true. All we can say is we cannot reject it, right? And if we reject this, we're saying this is true. So what we're really saying here is we cannot reject the alternative hypothesis, right? Cannot reject that. Let's see, wait a minute. We can't accept this. We cannot reject it, right? So what we're saying here is appears to be as consistent, right? It appears to be as consistent. We can't say they are as consistent. What we can say is they appear to be as consistent, right? Yeah, so if we reject, we're accepting the alternative, right? And the alternative is they're different, right? If we say we reject the null, we're accepting the alternative. And the alternative is that it's not as consistent. Or it's not, yeah, it's either less consistent or it's more consistent, right? All right, see if we get it right. Okay, so the evidence is suggesting that they appear to be as consistent. So we are okay with making, as long we know that our prices are less than Maytap, right? So that's the first claim. We know that is to be true, right? We don't have to test that because our list prices are lower than their list prices, right? But we made this statement here, just as consistent, meaning our variance equals their variance, right? So although we didn't get the industrial trade publications approval because we could only say that our ovens are the average is 350 degrees, we couldn't say our standard deviation was under 5 degrees. So we didn't get the industrial trade publications stamp of approval because we only passed one test. However, we can say our marketing that says our ovens are cheaper and as consistent as the industrial leader Maytap, we can say that because the results indicate that our gas ovens are as consistent as Maytap's.